Okay, I'm going to go ahead and get started. We've got a little bit of introductory stuff, so anyone who's a few minutes late is just going to miss that. Welcome to the webinar on In-Situ Sludge removal. I'm Julie Hartwig. I'm a lagoon specialist with Triple Point Environmental. So an overview of what we're going to go over today is some basics on who Triple Point is, if this is your first webinar joining us. Then we're going to go over some of the basics of sludge in lagoon systems, where it comes from, what it does. And then we're going to go over some of these sludge removal options that lagoon system owners and operators have. That includes dredging and offline removal, removal with bacteria in situ, and mixing and aeration in situ. And then our final main point of the day is a sludge reduction case study from a pilot program that Triple Point ran over a 12-month period in the last few years. This photo at the side is not lagoon sludge. This was taken at a dairy plant. It turns out it is kind of difficult to find photos to populate a webinar on sludge, considering our object of focus is under the water. So this is actually scum on the surface of a lagoon at a dairy plant. This is not a field. If you look at the grass around the edges, this is floating scum on a lagoon, which is as close to sludge as I can really get for you in a lot of these cases. So just some background on who Triple Point Environmental is. We are a lagoon services company, and this is our motto: lagoons do it better. This is kind of a guiding principle and a community that we're trying to start. We believe that lagoons are an important technology for treating wastewater, that they can not only keep up with modern permit limits and modern times, but they actually, in some cases, can even do it better than a mechanical plant. So we're trying to get the word out there and bring people who own and operate and work with lagoons together. We have not only this webinar series, but we also have a YouTube channel, Lagoons Do It Better, as well as a Facebook community, where if you join the Facebook community, we will send you a free hat if you're interested in connecting with other owners and operators. This is just a brief overview of the services that we offer at Triple Point. Our first product, starting from the left, is our Mars aerator. This is to provide lagoon mixing and aeration, and we're going to talk about that a lot a little bit later in this hour. These are drop-in units for lagoons that are already online or newly being built, that they can be dropped into an existing lagoon without needing to drain it or hard pipe anything. It combines fine bubble aeration with a coarse bubble release for mixing, and it puts all the moving parts on shore. These aerators are powered by blowers on the shore for easy maintenance because you don't have to go out in a boat. Our next product is our nitrox ammonia removal reactor. A lot of states are starting to impose ammonia limits on people's permits, and some of our other webinars have covered that there are limitations to treating ammonia in lagoons, particularly in cold weather. So we created a reactor to concentrate that process so it can run really efficiently. We can also, our next product, we can expand that nitrox reactor with additional cells to remove total nitrogen, not just ammonia. And our final system here is our PhosBox. It's a tertiary filter to remove lagoon phosphorus as well as TSS. So getting into the basics of why we're here. Anybody that's worked with lagoons, whether it be an operator or an engineer, encounters sludge eventually. Every lagoon has it, but where does it come from? It builds up at the bottom of the lagoon. Some of it comes from the influent, and then some of it comes from lagoon operation itself. So our first component of sludge is grit. This is going to be something that's coming in with your influent into the lagoon that settles out. And we're talking about grit, we're talking about things that are not organic. They are not biodegradable. Things like sand and silt and bits of concrete and metals. Things that are not going to be broken down, they're just going to settle out and lay at the bottom very inert. The next component of lagoon sludge are complex organics. These are organic in a chemistry sense. They're made of carbon and hydrogen, but they're complex. They're hard to break down. We're talking about things like paper or rags here, that theoretically they could be broken down, but it's difficult to do so. They're hard to break apart. They're hard for bacteria to digest. And bacteria are going to be lazy. If they have BOD in the water, if they've got compounds that are simple and easy to eat, they're going to eat those first, not these complex plant-based systems that are harder to break down. So those things settle out and then they become part of the sludge layer. And finally, this is often a majority of the sludge, particularly in later cells where you don't have the influent as much, is dead biomass. So in a lagoon system, you're growing bacteria. The bacteria community is what is doing the treatment in the lagoon. And eventually those bacteria, they eat, they reproduce, they make lots of new little bacteria, but eventually they die. And once they die, most of their bodies get recycled. They're eaten by other bacteria or by other life forms that prey on bacteria, but there's some things that are left over. Again, we're talking about stuff that's hard to break down, hard to recycle. You think about it, a bacteria dying in a lagoon, like an animal dying in a forest. The flesh is going to get eaten, it's going to decompose, but the bones are going to remain longer than the rest of the animal. And that's kind of a good analogy for lagoon sludge. The easy parts get recycled as part of the lagoon system, but the hard leftover stuff settles to the bottom as sludge. And then finally, part of the biomass can be non-bacteria. We're talking about things like algae or duckweed. This also can be leaf litter if you have trees that are overhanging your lagoon. If the algae or duckweed that's growing in the lagoon or on the surface dies, particularly all at once, whether it be due to temperature or a shock or an application of algicide, a lot of times that material will sink to the bottom and be part of the sludge layer where it's not going to be broken down into the water. And again, all lagoons are designed with sludge. It is a fundamental nature of lagoons. It's why you have the advantage where you don't have to handle solids every day like you do in an activated sludge system. But eventually all lagoons need maintenance. And unfortunately, this can be something that's easy to lose sight of because they don't need maintenance every year. They might be designed to have maintenance every 10 years, every 20 years. But a lot of times, by the time that maintenance need really comes to a head, the owners and operators or the town might not be ready for it. So what problems do you get when you have excess sludge in your lagoon? Like I said on the last slide, lagoons are designed to store sludge. Usually the bottom foot or two of depth in the lagoon is designed to eventually be filled with sludge. That's meant to leave you with enough of this supernatant or effluent layer, the actual free water in the lagoon, to give you the treatment that your lagoon is designed for. However, if you don't keep up with your sludge, or if something happens that it's accumulating faster than intended, then you start to get issues with an excessive amount of sludge. And the first one of those issues is reduced treatment. You are stealing water volume from your lagoon because it's being taken up by the sludge instead of by water where bacteria are actively performing treatment. This acts as a form of short circuiting, or if your lagoon was designed to have, say, 60 days of retention time, but a third of the bottom of the lagoon is taken up with sludge, now you only have 40 days instead, and you're just getting a proportionately less level of treatment. A very thick sludge layer also contributes hugely to odors. A lot of lagoon odor accumulates, it originates in the sludge, which is breaking down anaerobically. If you've got a healthy big layer of aerobic water on top, whether that be from a facultative lagoon or an aerated lagoon, a lot of times that odor is decomposed on its way bubbling up through the liquid and isn't a big problem. But if you've got a thick sludge blanket, or you've got so much biomass in the sludge blanket that it's producing odor too fast, some of it's going to escape, and then you get complaint calls from the neighbors if you have any. Another problem you can get is lagoon turnover. If you've got sludge building up and your lagoon isn't well mixed enough to prevent temperature stratification, then you get turnover in the spring and the fall, where you get thermal inversion, your liquid layers move around, and that can help bring the sludge to the surface. Again, that can introduce a lot of odors, and that can also put in a lot of TSS into the water during those transitions between seasons. And finally, this is a constant problem with sludge, but it gets much worse with an excessive sludge layer, is benthal feedback. Benthal feedback is all of the nutrients, all of the history that's stored in the sludge can be released back into the water from the sludge layer. And that can mess with your treatment goals, that can mess with your nutrient limits. And a good example here I saw a few months ago. I was at a lagoon that had installed one of our ammonia removal reactors, and we were doing testing across the system. We were testing for ammonia coming out of the reactor, and the ammonia level was non-detect. It was nearly zero for our field test. But that reactor discharged into a third cell that had existing sludge from the days before the reactor was built. And we tested in that third cell, and we tested in their effluent, and the ammonia level actually rose as it went through that final polishing cell. It went from 0 in the reactor up to about a half. It wasn't enough to mess up their permit, but the ammonia actually came back into the water after it had been removed, because there's ammonia present in their sludge. And as the water is mixed via aeration or wind or what have you, it was feeding back into the water. A lot of times this isn't an issue in a lagoon system that's operating properly, but if you have very strict limits, or if you have sludge issues, this can start to throw your effluent quality out of whack. So we'll just do a quick review of sludge biology, what's going on down there that it's causing these odor issues and other issues. And your sludge layer is basically a separate habitat for bacteria within the lagoon. This habitat is going to be anaerobic, as opposed to the water on top, which might be aerated by mechanical aeration or by algae during the day or by wind action. You're not going to have oxygen down in your sludge layer. And that plays host to a big community of different bacteria that are still working on breaking down anything they can that settles down there. Anything that's organic. They're not going to break down sand, but they'll try to break down rags and paper and dead bacteria. But there's a couple species that are worth noting because their effects are the most noticeable. The first one are acid-forming bacteria. These are the first half of a symbiotic partnership with those bacteria and bacteria who make methane. The acid-forming bacteria break down organic molecules into organic acids like acetic acid, which is vinegar, or butyric acid. So the pH in the sludge will tend to be much lower than in the lagoon due to these acid formers. The next bacteria species are methanogens, methane-producing bacteria. And what they need is they use the acids formed by the other bacteria, particularly acetic acid, and they make methane. This is a byproduct of breaking down carbon-bearing molecules. In an aerobic system up above, they'll break down carbon molecules into CO2, which off-gasses. Similar process happens in the sludge, but because it's anaerobic, it becomes methane. Some of that methane might get converted as it rises through the water column, but some of it will off-gas as CH4, just pure methane. And the final species of note in the sludge are sulfate-reducing bacteria. These are bacteria that, in their metabolism, they use sulfur compounds as kind of a substitute for oxygen because no oxygen is involved. And the byproduct they make from this metabolism is hydrogen sulfide gas. And this is the odor that we're all familiar with. It smells like rotten eggs. The most significant contributor to odor in a lagoon comes from hydrogen sulfide made in the sludge layer. So all of this together, what does that add up to? This community is good for reducing the sludge blanket. You want to have your sludge be alive. Otherwise, it will build up a lot faster than it does if those bacteria weren't constantly chewing away at it. They're slower than aerobic bacteria, but they're always working. If there's something there to eat, they'll eat it. But the bad news can be if it's out of whack, if there's too much of it, it's too near the surface, you get odor. And then if you have a lot of methane-based bacteria, you can get floating sludge. It can actually help lift chunks of sludge to the surface of the lagoon. So now that we've gone over the basics of sludge, how do you tell what sludge you have in your lagoon? Maybe this is just because you're curious, or maybe it's because you've noticed you're experiencing problems with the lagoon and you believe sludge is playing a role because your lagoon hasn't been dredged in maybe 20 or 30 years. We see a lot of the time. You need to perform a sludge survey, which involves usually somebody going out on a boat and figuring it out. So our first recommendation for performing a sludge survey is to grid it out. Make a plan for where your sludge testing sites are going to be. This is particularly important if you're trying to do a before and after study. You want to make sure you're comparing apples to apples, that you're testing in the same place each time. But it's also just good to have a plan to make sure you're getting a representative sample. So if you can, we recommend that you create permanent marker points on the banks of the lagoon rather than just estimating, oh, this line is halfway across the lagoon, or we were going parallel to the effluent structure. You can do something like pound a wooden stake in at the edge of the lagoon berm, paint it a bright color, and that becomes your grid for tests now and future. And if you're really scientific about it, you can string a rope across the lagoon between those two grids to make sure you're actually on parallel. Unfortunately, performing sludge surveys, I've seen you can be really susceptible to wind blowing you off course, where you might start measuring at the place that you intended, and by the time you're done measuring, you might be 20 feet away. So that's just something to be aware of, is trying to stay in the same point for each of your tests. So then what do you use to actually perform the sludge survey? The most common method, demonstrated in this picture by my coworker Tom, is using a sludge judge. These are widely available, used in multiple kinds of waste treatment plants. A sludge judge is a clear plastic tube. It has level markers, measuring markers, usually at 1 foot intervals, marked along its surface. And then it has a foot valve at the bottom that closes under gravity when the sludge judge is full of liquid and sludge, so you can raise it up and see what you're dealing with. So the basic method is you've got to start with an empty sludge judge, and you slowly lower it down through the water until you contact the sludge blanket. It'll fill with water and then with sludge as it passes through. And then typically in a fluffy sludge blanket, like an activated sludge clarifier, you can push the sludge judge all the way to the bottom of the water and actually see, when you pull it back up, how deep your sludge layer is. Unfortunately, this can be problematic in lagoons because the base layer of the sludge in lagoons is often very dense, very compact. And if it's very deep, you're going to have a hard time getting multiple feet of sludge to slide easily into an 1.5 inch diameter tube. And one for sure sign that that's happening is if your foot valve starts to clog. If you watch the water in the sludge judge, if the foot valve starts to clog, the water will actually dip below the real surface of the lagoon as you continue to push the sludge judge in. So another way of using a sludge judge that works better in lagoons is you just use it as a probe to feel for the top of the sludge blanket. You're not trying to push it all the way through to the bottom. You're trying to figure out where the boundary line is between water, where it's passing through easily, and sludge, where it starts to meet resistance. Then you can stop, take your measurement for how deep you pulled in the sludge judge. Now you know your free water. And then if you know the depth of the lagoon, you subtract that out. So if your lagoon is 10 feet deep and your sludge judge went in 8 feet before hitting resistance, you've got 2 feet of sludge in the bottom. One other thing that helps ease the problem of sludge judges getting clogged, particularly if you're trying to take samples of the sludge at the bottom of the lagoon, is to buy or build a wider sludge judge. Typically, they're 1.5 inches, 2 inches wide, but I have heard examples of people making it out of 3-inch clear PVC. They DIY it, and that much wider sampling diameter can get you a much more accurate core sample because it reduces friction between the sludge and the inner sides of the tube. Another way to do a sludge survey is using sonar. Some companies make purpose-built boats for this, but people have also used depth finders like you would for fishing. These can be very advantageous because instead of just taking point samples like you would with a sludge judge, you can get a profile where you run the sonar system across a line in the lagoon and you get a continuous measurement. And at the higher end, you can even, some of them can do a 3D map of the surface of the sludge in the lagoon. Another method, another point method that's very accurate is an ultrasonic probe. This is a probe that you lower down into the water and it's set to alarm when it hits a certain density of solids. This can be helpful for finding the top of a fluffy sludge blanket that might not be dense enough to stop a sludge judge. The problem with ultrasonic probes is they tend to be much more expensive than these other options, where a sludge judge might be $100 to $150. A lot of these ultrasonic probes are in excess of $1,000. So maybe you're not going to buy one just for your plant, but that might be something to talk to a local circuit rider about and see if someone has one that you can borrow for sludge surveys. And then a final method is using a Secchi disc. That's pictured in the picture that just popped up. These were designed originally to measure turbidity in ponds and lakes. It consists of a metal disc that's painted with this cross attached to a rope. The original theory was to measure turbidity. You lower this disc down into the water until you can't see it anymore. In lagoons, it tends to become invisible almost right away. They are not clear like you'd expect a lake to be. But if you're using them for sludge judging, you can use them in a different way, which is to lower it down until it stops sinking. Once again, this is a measurement to the top of the sludge blanket. Once that disc settles on the sludge blanket, the line is going to go slack. It's not going to sink anymore. And then you can pinch the line at the surface of the water and measure how deep it went in before it stopped. This is a pretty user-friendly and very cheap way to do this. Secchi discs are available for $25, $30 at many places. So if you're looking at doing a sludge removal project, the first step is to do a sludge survey. See how much sludge you have in your lagoon, make a map. But then how do you evaluate how you're going to remove it and how much that might cost? In that case, it's very helpful to have testing done on the sludge to see what it's made of. So this is done by taking a core sample or hopefully multiple core samples using a sludge judge. You push it down into the sludge layer and then you release the sludge from the tip of the sludge judge into a sample bottle, send it off to be sampled. And what the lab will do in that case for sludge testing is they'll test the amount of solids that are present in the sludge. This is how concentrated it is. The more solids you have, the more milligrams per liter of solids, the denser it is. This can be more efficient to remove, but it's also thicker and can be more difficult to dredge or to pump. And then the second test that is very important for in situ removal is a test for how much of the sludge content is volatile. This is a test of how you differentiate organic solids, things that can be broken down, from grit, things that are not going to be able to be broken down in situ. The way that the lab will test that is when they are doing the total solids test, they'll filter the water, they will measure the weight of a dried cake of solids. That's your total solids. Then to get volatile solids, they bake that sludge cake in a very hot oven for a prescribed amount of time, and the organic solids will burn away. Organic molecules, dead bacteria, paper, stuff like that will gas off, and what's left is just the non-volatile solids. So the difference between your total solids and what's left over after baking is the volatile solids content of your sludge. And that's important to know as a whole number, but it's also very useful to know as a percentage, which you can calculate from those two. So in this case, example calculation, you have the roughly 17,000 milligrams per liter of volatile solids over 35,000 milligrams per liter of total solids times 100. And this sludge sample was 48.6% volatile. So if we're talking about in situ removal, which is breaking down volatile solids as much as you can versus having to remove the grit, you've got about half your sludge blanket to theoretically play with, is what this sample says. So very powerful tool, big predictor of how successful you're going to be. And the total solids is also very helpful if you're looking at dredging, not doing in situ removal, because that can help you, an engineer, calculate what are your total dry tons that you have to deal with disposing. They'll need to know that total solids number. So let's get into sludge removal options. This photo was taken at a lagoon that was actively being dredged. That's the dredging boat on the lagoon. That lagoon was still in service. So this is not in situ sludge removal yet, but we're just going to go over the alternatives first. So the most popular form of sludge removal that I have seen is dredging. This removes all the components of the sludge. This is the total solids, the grit, the volatiles, all of it. As in this illustration, you send a boat out on the lagoon that has a cutting suction head that runs along the bottom to break up and suck up the sludge that's pumped to the shore, where it will have to be dewatered. You might have 4% solids, you might have 6% solids. That's mostly water that would be extremely expensive to haul away. So the dredging company, the dredging crew will have some kind of dewatering device, whether that's a belt press or a centrifuge that you need to add chemical to, or if the site is building drying pads, you're going to want to dewater the sludge somehow. The advantage of dredging is not only that it removes everything and can almost completely rehabilitate the lagoon back to like it was built, but it allows you to keep the lagoon online. You don't have to drain it, you don't have to mess with it. But the problem is it tends to be extremely expensive. We're talking hundreds of dollars per dry ton, depending on where you are in the country and what your disposal options are. On a multi-acre lagoon system, that can easily run upwards of $1 million, which, considering lagoons are often in small municipalities, a lot of those don't have that in the budget unless they've been saving up for it. It can be a kind of a shock expense. Even if you do have the money, some things to be cautious of, some stories I've heard, is the first one is the problem of how do you dispose of the sludge. This is a kind of a hazardous product. It is human waste, it has pathogens, and it's got a high water content. So what do you do with it? Landfilling is an obvious solution. You need to have a landfill that can take the sludge. I know of a lagoon that has a landfill 10 miles away, which seems perfect, but the amount of sludge this lagoon is going to produce when it's dredged is equivalent to 3 years worth of the total intake of the landfill. And even if they were capable of laying that down over the couple months of the dredging project, they're worried about the stability of the landfill itself. They're worried that they're going to end up with a mudslide of sludge. So they said they can't take it, even though, or they can't take most of it at least, even though they're only 10 miles from the site and they have the space for it. Other disposal options can include land implying. That's its own, you got to find land, you have to figure out your hauling costs, and then there's permitting issues with that as well, because you have nutrients in the sludge that you need to keep from running into waterways. So there's not a lot of one-size-fits-all solutions for what to do with your particular lagoon's sludge. Another thing is take a key look at your contractor's qualifications. There's some companies that are professionals at this, they do it really well. But there's also companies that think that they can do it. They're in a similar business, they throw in a bid. And if they're the low bidder, possibly great. But I've also heard stories where they've had manpower shortages or equipment failures. They've blown their timelines. What something is supposed to take 2 months, it takes 8 months. So take a look at your low bidders to make sure all of your contractors are qualified. Another one is labor availability. This kind of goes back to the contractor qualifications. Point is, I've heard of a crew, a bidder says, hey, we're going to hire local people to run our dredging crew. That's great, says the town, going to create jobs locally. But it turns out dredging is physically intense, nasty work. And not every town has a population of people who are physically capable of working outdoors with heavy equipment for that long, are willing to do it for months at a time, dealing with stinky wastewater sludge, and are willing to do it and available to do it for the wages you're willing to pay. So that can be an advantage. It's expensive to bring in a crew from out of town, put them up in a hotel, but it might be worth it in the long run. And then the last problem is performance expectations. All of this dredging is taking place where you can't see it. And that can be problematic because whether through foul play or just through honest mistakes, dredging heads can do things like push the sludge off to the sides instead of sucking it up. So they do all their passes across the lagoon, they suck it up till they get clean water and they think, great, they're done, you've dredged this lagoon. And then you go back and test it and the lagoon has just about as much sludge in it as when you started. So if you're writing a contract, put performance expectations in there as to how much sludge will remain when they're done for the contract to have been fulfilled. The other option for ex situ true removal is offline removal. This is when you bypass around a cell of the lagoon, you drain off all the water, and then you remove the sludge blanket. So instead of dredging it out from under the water, you take the water off the top. This is somewhat easier to get right than dredging because you can see what you're doing. If you don't have liner concerns, you can get down into the lagoon with heavy equipment. So instead of suction pumps, you can go in there with excavators or bulldozers. You're going to face all of the same disposal problems. The photo on the side was a lagoon that had the sludge being removed. It was being dried on a belt press, and this was the output of the belt press, creating piles that were waiting to be hauled off site. I have heard of offline removal in lagoons out west that have a hot climate and not a lot of rainfall, can try to dry their sludge in place in the lagoon itself. This can avoid the expense of building drying beds or renting dewatering equipment. But a note there is to make sure to windrow the sludge and turn it over reasonably frequently. Sludge is really good at drying out just on the surface, so it looks very desiccated. And then you go to move it, and it turns out it was just on the surface, and it's still wet and mucky underneath. And finally, we get into our in-situ sludge removal options. This is a very different type of removal than dredging. This is only going to affect the volatile portion of the sludge. Unfortunately, there is no magic way in situ to degrade sand and silt and grit. We're just going after the volatile organics that can be broken down. The good news is it's usually much cheaper and easier than physically hauling the sludge off someplace. There can be a more immediate performance improvement. So if you're suffering from treatment issues due to excessive sludge, this can get you back into compliance a lot faster because you don't have to wait for a crew to get on site, wait for bidding, etc. And then what this can do really is it's buying time for you to budget for complete removal. You cannot, unless you've built a weirdly extra deep lagoon with infinite sludge storage. This isn't the final answer. Someday you're going to have to dredge or drain the lagoon to get rid of the grit, but this will buy you years at a time in order for you to budget and save up to do the real removal. So the first of the two methods we're going to be covering is bioaugmentation. And I should note that these methods are not mutually exclusive. They work great together. So the first method is you're adding bacteria to the lagoon specifically for the purpose of removing sludge. Many companies out there make these blends, and these are bacteria that are bred and developed and custom made to eat the complex organic compounds and dead bacteria that are sitting down there in the sludge. They're supposed to do a better job of it than the bacteria that naturally come up. That's what you're paying for here, is you're paying for the stronger bugs, that they're hungry, this is what they want to eat, they're good at it, they're going to get down in there and they're going to start eating up your sludge in place. These can remove a majority of the volatile portion of your sludge. They're not going to ever remove 100% because bacteria just aren't that efficient, but they can remove a majority of the volatile portion of the sludge, which can equal 30 to 60% of the entire sludge blanket. So we're talking a significant difference here. These are available in liquids that you inject, powders. I've heard of it in spikes that you can drive down into the sludge. Whatever manufacturer you go to will have their system for applying this. And then the final in situ method is removing sludge via aeration and mixing. This is a method where you're physically stirring up the sludge blanket so that you can use the treatment capacity of your lagoon to break down the volatile portions of the sludge. You're using your existing biomass to consume the volatile solids, and you're introducing oxygen usually into the sludge. That's one thing to note, that if you go and mix it up and let it settle right back down, oxygen is toxic to the anaerobic bacteria that usually live in the sludge. So if you're going to start mixing, you're going to want to keep mixing and do it aerobically, because you can really mess up the anaerobic natural process if you get a lot of oxygen down in there just for a short time. It'll take a while to recover. So how can you do this? One way is if you already have aeration or mixers in the lagoon, you can move them to a different place in the lagoon. Maybe they're keeping a small area clear of sludge, and if you move them, they will start mixing up sludge that's settled over there, and that'll help break that down and degrade it further. Or if you don't have aeration, or if you have aeration that's not very efficient at mixing, you can buy new products, make that part of an upgrade when you're going to add new aeration into a lagoon. So our pictures on the side here, this is the triple point Mars aerator. So this, for anyone who's not familiar, our aerator combines on the side here our fine bubble diffuser tubes. These are taking care of the aeration portion of the equation. There's millions of fine bubbles, have a huge amount of oxygen transfer. They're adding a lot of DO into their lagoon, and they're providing some mixing as they rise to the top. But we've chosen to combine the fine bubble aeration with a coarse bubble release in the center of the unit. The advantage of coarse bubble is that it provides a really powerful amount of mixing at the expense of oxygen transfer. So we used both. We used this coarse bubble mixing in the static tube at the center of the unit because that creates a draft effect, like an airlift pump as it rises through the static tube. And what it does, what you can see in the higher picture, is it pulls water in from beneath the Mars unit and it shoots it out the top and it mixes it back into the water column. So as you can imagine, if you drop one of these units into a sludge blanket, that the sludge underneath it is going to get mixed back into the water column where it can be degraded and broken down into a smaller amount of volume. And that's exactly what we're going to go over in our case study. So this case study took place at a food plant over the course of a year. This was a pilot project that Triple Point did in partnership with this plant. So the background, this is a plant in the southern US that produces cooking oil, culinary oils, and they have a very large lagoon that was incredibly choked with sludge. It was nominally about 15 feet deep, but in many places in the lagoon, they had more than 10 feet of sludge. So they had removed the majority of their treatment capacity from their lagoon with all of the sludge buildup because there just wasn't enough room for water in the lagoon. Their hydraulic retention time, their detention time was a lot shorter than it was designed to be. And then we'll show you a photo of this, but the layout of the lagoon, this was one very large lagoon, hundreds of feet in each direction, divided by an existing baffle into two different cells. And then this was on the side, this is just another photo of the Mars aerator that we used on the site. This is an example of computational fluid dynamics. It was a computer model that we did of the water in the air interacting with the Mars unit to show the kind of heat map of how it's pulling in water and sludge from underneath itself. All these little arrows represent water flow, and the colors represent the relative strength. So it's keeping A, the tubes clear of the sludge, and B, pulling in sludge from under itself and mixing it back into the water column. And that's the effect that we're going to rely on when we designed our aeration pilot at this plant. So our design, first we added an additional baffle to create a pilot cell. So this image on the right is an up-to-date Google Earth image of the plant. You can see the bottom edge of the stripe down the middle was the old baffle, and then the top edge was a new baffle. So we're creating a pilot zone that's free of the influence of their existing surface aerators, and they are installing 20 Mars units in this pilot cell in the center of the lagoon. And the goal here eventually would be to provide treatment increases, but that's hard to measure when you've got a small pilot cell and you've got surface aerators and tracking your ins and outs. So the initial goal of this pilot was to study the effect of the Mars units on the sludge in the pilot cell. So to measure that, we performed a sludge survey before we installed the Mars aerators, and then we performed surveys after the aerators were installed and turned on to evaluate their performance. So what we ended up doing is doing a survey at about 2 months after installation and a year after installation to compare the sludge levels. And like I said before, very important part of a sludge survey process is to grid it out, to create a map. So you're comparing apples to apples, making sure that we're doing a correct comparison of which sludge depths where in the lagoon. So we created a grid of 18 points. These points were designed to be the midpoints between our 20 Mars aerators. The aerators were put in 2 lines of 10 down the center of the pilot cell. So we have 2 lines, A and B, and then we have our cross-testing points, 9 of them per line between each unit. That creates our grid of 18 testing points. So here's a survey of a picture of our final sludge survey being done. This was a fishing kayak with a trolling motor on it. So you don't need any specialized type of boat to do this. If you've got a boat that you're willing to float out in the lagoon, you can make it happen, even if that boat is a kayak. So here is our crew out in the lagoon. Our primary measurement was using a sludge judge. We used it in the way where we were not trying to go to the bottom of the lagoon. Their blanket was just too deep. Instead, it was just lowered until they could meet resistance. And then that was measured. That was the depth of the free water on top of the sludge. And then we subtracted it from the total lagoon depth to find the sludge blanket depth. At some of the points, we also validated that measurement using a Secchi disc. So that was lowered down again until you can feel the top of the sludge blanket in order to double check our work and see if they were in agreement, which they usually were, and if they weren't, we retested until we found an accurate answer. So here's the big reveal. A lot of numbers over here on the left from our 18 different testing points and 3 different sludge surveys. But the averages in the bottom, I think, tell the story that we'd wanted to tell. Our average reduction in the depth at each point was 36%. As you can see from above it, not every point was reduced evenly. Some of them got slightly deeper. Some of that just might be resettling sludge if that point was abnormally low before we turned the aerators on and they leveled out the blanket a little bit. Some of them went up slightly, and then some of them had 100% removal where that sludge judge went all the way down to the bottom of the lagoon. That Secchi disc went all the way down to the bottom of the lagoon with no resistance because we had moved all the sludge away. So our median sludge reduction, a little bit more accurate, was 44.4% removal. Our final number that we concluded going by total volume of the lagoon, not just by each individual cell, was 44.3%. We removed 44.3% of the sludge in this pilot cell in a year just by operating our Mars aerators. They did add bacteria as well to give them a boost, but no sludge was physically taken off the site except for a couple small samples. And what does that actually look like? Over on the side here, we've got a graph of the 3 different surveys to create a more quick visual of what that reduction looks like. So the blue in the back was the original survey, the highest depth. The red was the survey 2 months afterwards. And the green was the final survey, where much lower on average. You can see visually how the sludge was reduced. But when I put this graph together, I noticed something interesting, that over on the left-hand side of this figure, it's very zigzaggy. As we're going from A to B to A to B to A to B, it was seesawing back and forth. I was curious what that effect was, so I decided to create new graphs, dividing that sludge profile up by rows. And those are illustrated here. I thought that was really interesting. I was glad I divided them because you've got a very strong effect that you've seen now. In row A, closer to the old baffle, our total removal was over 60% along that line of testing. So you can see the blue and the red are the original 2 sludge surveys from December and February. And then the green is hugely reduced 1 year later. On row B, it was a different story. Blue in the background is reasonably similar on average. The red survey done in February was weirdly low. I honestly don't have an explanation for that. And then the final survey was reduced. It was reduced closer to 12%, not the 60+% we saw in row A. And to help illustrate what that actually means when we look at the lagoon itself, is I mapped each of the test zones onto our grid itself. So the greener a cell is, the more reduction we got. So the 100% removal cells are the darkest green. And then some cells where we went negative and the sludge actually increased are in red. So you can see along line A, we're green up until the end. I think we might have created a bit of a dead zone down by A9 because that got much deeper, or maybe there was a weird hydraulic situation with an eddy that built up sludge there. And then along line B, we have more modest reductions or small increases in the sludge. So we talked it over, everyone who was involved, trying to think of what's the explanation for this. And the best that we can guess with the data that we have is that water in this lagoon flows from right to left. So it enters the pilot cell near the top of row B. And maybe because it's hitting a zone of higher DO without as much dead spots, this pilot zone is very, very heavily aerated. We might have had a boost in treatment that was creating solids at about an equivalent rate to the sludge reduction rate. So maybe that kind of zeroed out the sludge reduction along row B. And then row A, this water had been present in the cell a little bit longer, so the reduction effect was less canceled out there. To be honest, one of the other theories that we considered was that row A is nearest to the old baffle, and we don't know what kind of shape that baffle is in under the water. So we considered that maybe the sludge was just being shoved from the pilot cell into cell 2 through holes in the old baffle. But the reason we ruled that out was if we go back up to these row graphs, you would think that if it was just a physical effect that it was being blown into the cell next door, that would have happened very immediately. That air turns on and sludge starts to move really fast. You're not waiting on biology. But look at the difference in December to February in row A. If it was all just blowing over the curtain, you would think it would have blown over by February when the aerators had been on 2 months versus 12 months. So that's why I think it's probably treatment influenced rather than just a physical, it's being moved elsewhere. So that's our map. These average out, like I said, to 44.3% reduction. That's over a 12-month period. That's over a lagoon that was more than 2/3 full of sludge rather than water. So if you look at the physical volume that we removed of sludge, we increased the water volume in that pilot cell. We increased the water in that pilot cell by 72.4%. That's a huge boost in treatment compared to what they were used to. If you applied that across the whole lagoon, you're almost doubling your hydraulic retention time, you're doubling your treatment volume or increasing it by 70%. That would solve, I believe, a lot of people's problems having a 72% increase in treatment volume. And then compared to dredging, this would be again across the whole lagoon, not just the pilot cell itself. Aeration, we calculated, would save them, with these reductions, $146,000 in dredging costs. That's what it would have cost to physically remove the sludge that we reduced just by turning aerators on, aerators that they needed anyway. That was based on a rate of 7 cents per gallon of sludge removed. Typically, you would see pounds per dry ton of sludge removed, but this was another figure because we didn't have enough data to accurately calculate the dry tonnage. But that was our initial payback, $146,000 worth of dredging avoided 44% sludge removal in a year. So that's my conclusions from my case study. Do we have any questions? I have one question. I've got a couple of them. I'm sorry, I don't believe there's a way to let you guys ask your own questions live on the microphone. Someone asked, was this food plant lagoon a facultative lagoon before? I don't believe so. I think this lagoon has been aerated for its entire history. I do think they have had problems with their surface aerators in the past, not always being completely online. I think they've had some of them drift over to the sides of the lagoon. They weren't necessarily tethered strongly enough, so you get dead zones, and that's how you get a lot of this sludge increase. Hang on, I'm fighting with the software a little bit to read this question. People are asking if you could use aerators in a facultative lagoon. Won't the oxygen kill the anaerobic portion of a facultative system? The answer is yes. If we put aerators in a facultative lagoon, it is just not going to operate as a facultative lagoon anymore. You're going to have a much reduced anaerobic portion of a lagoon going from a facultative lagoon to an aerated lagoon. You're not going to have free water near the bottom of the lagoon that's anaerobic. All the water surface will be aerobic. So it would just be a very different operational mode. But we have seen plenty of people add aeration to a facultative lagoon because more DO, particularly overnight, when algae aren't going to help you, adds a lot of treatment capacity. So it's so much so that it's worth it. So I've got a question. Did we measure volatile solids reduction? We tried. Unfortunately, on a percentage basis, the results didn't make a whole lot of sense. It looked like the volatile solids percent went from about 36% to start to about 48% to stop, which is the opposite trend than we'd like to see. But I believe overall, the second sample that we took was much lower in TSS entirely. So that was probably newer, fresher sludge on top. So we need to go back and take another core sample to get a really representative answer, because we managed to remove sludge, but at least from the samples we took, it looks like the solids percentage went backwards. We've got a question. Do regional service organizations provide dredging services in other portions of the country, as was done in certain areas of Missouri some years ago? I am not sure. If you're talking about private companies, I know every region has got a few dredgers, that's their business model. But if you're talking about other organizations, we would have to get back to you. I'm not sure how to answer that one. Question, what powers our Mars aerators? Our Mars aerators are powered by blowers sitting on the shore. Those are usually PD blowers in their own enclosures. You can see in my questions screen, that's that little hut next to the aerated zone. This plant is large enough that those are turbo blowers, but that's how they're being powered. That's just airflow. There's no electric under the water. There's no moving parts. It's just air being diffused that's being pushed on shore. Largest municipal lagoon treated in situ. I do not know how large the lagoon. We've studied sludge reduction. Our largest lagoon ever by acreage is the one pictured on this question slide. I believe that's a 70-acre lagoon system. And I think by MGD, our largest treatment system was 7 MGD. And that plant, we might have data on sludge. I would have to get back to you. That's a great question. When you reduce the sludge, is there any ammonia feedback? Yes, there definitely can be. So far, a lot of times we are putting these aerators in far enough at the head of the plant that ammonia feedback is removed by the time it gets to the end, or a lot of the aerators we've put in over the years have been in plants that didn't have an ammonia limit, but there absolutely is an issue where you're going to release the nutrients that are in the sludge when you put it back into the water. That can be ammonia, and that can be anything else, BOD, that's hiding down there, TSS for sure. So if we continue with the case study, do we expect higher sludge removal after 1 year? We're definitely continuing. They're operating the pilot. Those are their aerators now. They continuously operate. I would like to get back in there and take more data. I'm not sure, like I said, our volatile solids testing, we've got 2 samples. I don't think they're quite apples to apples samples, so I'd like to take some more. It's possible that we're going to expect higher sludge removal after a year, but it's going to slow down in rate considerably, I would expect. That we've done the majority of it, and then it just might be maybe a few more percent over time. I've got a question here. What about wetlands? I have cattails at the end. What is a way to clean them? I was actually last Friday at a lagoon system that has wetlands at the end full of cattails, and those, you're not going to be able to drop an aerator in those typically. They're too choked with plant life. A lot of times you're just going to have to get out there with an excavator. That was actually a study that's being done at the plant that I visited by some PhD students at a university here. So wetlands are a whole nother beast. If you've got plant life in the lagoon, you might actually just have to physically dig those out. Question, how do the augmented microbes compete with microbes that are already established in the environment to consume the sludge? A lot of times the microbes that are being put in there are kind of living in a solution of nutrients. They are primed and ready is when they go in there. So they are already at their peak. They're not competing for oxygen is important. And then they're also not really competing for food. They're going after the food that nobody else wants. A bioaugmentation company might be able to answer that question in more detail. If you'd like us to follow up with that, please let us know. With aerators, have we seen issues with high TSS and lagoon effluent with these aerators? Maybe briefly when we put them in, if they're starting to disturb the sludge. But again, usually we're putting most of our aerators at the head of the plant. That's where they're needed to do their job to reduce BOD. So the rest of the lagoon system acts as settling. And then over time, we've not noticed over time sustained increase in TSS in effluent when you go to an aerated system. Another question, do we need some sort of mixing if you're adding bags of bacteria? Again, I'm going to leave this up to the manufacturers. Typically, mixing helps. Steve Harris of, I think H&S Environmental is his company. He recommends that if you're doing mixing to kind of supercharge adding the bags of bacteria, he's seen setups where you drag chains behind a boat to rustle up the surface of the sludge layer. That can help a lot. So I don't think it's strictly necessary, but it can help you get more bang for your buck, I believe. So how should you budget for sludge removal and wetlands dig out? So if you're doing ex-situ sludge removal, and this is getting into, I've learned this from talks at shows I've been to, not because I've done it myself, but an engineering firm is going to have to do a study on that. Estimating sludge removal is a pretty exacting process because it's one thing to say I've got 10 feet of sludge in this portion of the lagoon, but then what's the solids content? Is it 4% all the way down, or is it 2% at the top and 8% at the bottom, and when does that change? So when you're calculating your total dry tons expected to remove, that's going to control your sludge bidding number. And that is something that you need a pretty sophisticated engineering study to get right. And I would assume they'd be able to help you with wetlands as well. Question on the 146,000 in savings. Does that mean if dredging would have cost $1 million, does the air cost 850,000? No, that was strictly, that was not including the electric cost. The electric cost was not $850,000 here. I don't have that number off the top of my head. The $146,000 in savings was strictly that's what you have had to pay somebody to get out there and suck it out of the pond with a dredge, using the rate of 7 cents per gallon. Comment for one of my coworkers on one of the reasons that the core samples necessarily didn't have the results we expected. One of them was not immediately sent to a lab, so the biology was continuing to work after being disturbed in a bucket. Ideal samples handling is that you put it in your sample bottle, you get it in the fridge as fast as possible, and you get it to the lab as fast as possible. And that I don't think necessarily happened in this case. Power cost savings question again, savings in dredging cost. That's a little bit of an apples to oranges question. The power cost is far cheaper than dredging. And then you're also looking at the apples to apples comparison is running the Mars aerators versus running the surface aerators. Surface aerators aren't as much help with sludge reduction, and typically our Mars aerators can save power versus surface aerators up to 50%. Typically 50% less power used in our diffused aerators than running surface aerators. So oxygen, pound per pound for the oxygen we're adding, they're saving money on electric, and then they're just avoiding the dredging issue entirely. Okay, I'm sorry, questions keep pouring in here. Unfortunately, I am out of time. We are over our hour limit. So I have a list of your questions. We will follow up by email with a list of the answers to these questions. Thank you so much for your participation. I'm very happy that you have questions. I hope you've been satisfied with the answers thus far, and we will get back to you if we didn't make it to your question in time. So thank you so much. Have a great rest of your week.